Hey guys, today we're going to be talking about the idea of pH. So pH is going to be an important concept in grade 12 chemistry, and it's something that you might have heard of in grade 10 chemistry. You would have looked at the pH scale and figuring out if something's acidic and if something's basic. Today we're going to look at the mathematical basis behind the pH scale. Before we get into that though, I just want to revisit the idea of acids and bases from last week. Last week we looked at the idea of an Arrhenius acid and base. We said that based on Arrhenius, acids have an H plus and bases have an OH. Now we're going to take a look at one more theory that we didn't look at last week. This theory is a little less stringent. This theory is going to be called the Bronsted-Lowry theory of acids and bases. So if we're looking at Bronsted-Lowry, Bronsted-Lowry says that acids are proton donors and bases are proton acceptors. I want to be clear, and when we're talking about a proton, we're actually talking about an H plus ion. So Bronsted-Lowry says it doesn't so much matter if something has an H or an OH, it matters if it's giving up a hydrogen or if it's accepting a hydrogen. So let's take a look at this reaction here. In this reaction, based off what we knew last week, we don't see really an H at the beginning or an OH. So we might think that this is not an acid-base reaction. In all reality, this is a very common acid-base reaction, one that actually happens in your house involving ammonia. So let's take a look at this reaction based off of what Bronsted-Lowry said. So if we take a look at NH3 and if we take a look at H2O, we want to take a look at the change before the reaction and after the reaction. Let's focus on water to start. So water was H2O. And then on this side, water has now become OH. How are they different? They're different because water has given up a proton. Water's given up an H, right? So in this case, water's no longer H2O. It's only OH. It's given up one of those H's. Since water then donated a proton, we say water is an acid. NH3, let's see how NH3 is different. On this side, NH3 has 3 hydrogens. On this side, NH4 has 4 hydrogens. So how they're different is in this case, NH3 has gained a proton. It's accepted a proton. So we would say that this is a base. The other thing that's different about Bronsted-Lowry is we get into this idea of conjugate acid-base pairs. So when using the Bronsted-Lowry concept for acids and bases, we consider all acid-base reactions as reversible equilibria. So essentially what that means is not only do we have a base and an acid on this side, we have a base and an acid on this side too. So if this reaction wants to run in reverse, it's going to have an acid and base on this side too, because on this side we also have something accepting a proton and we have something donating a proton. This again is going to be an entire unit in grade 12 chemistry. So the challenging part of this lesson is determining when something is an acid and when something is a base. So let's take a closer look at these conjugate acid-base pairs. So we already identified that NH3 was a base on this side, and we identified that H2O was an acid on this side. Well, any acid has a conjugate base, and any base has a conjugate acid. So again, let's focus on H2O. H2O was an acid, so on the opposite side, it's going to be a conjugate base. So H2O on this side was an acid. That means OH on this side is going to be a conjugate base. The reason because of that, if we read this reaction in reverse, if we read OH change into H2O, let's think about how they're different. OH has 1 hydrogen on this side. H2O has 2 hydrogens on this side. In this case, the difference between OH and H2O, OH is accepting a hydrogen, right? OH is going from 1 hydrogen to 2 hydrogens. It's accepting a hydrogen. That means it's acting as a base if this reaction runs in reverse. The exact same idea with bases. Bases always have conjugate acids. So NH3 is a base on this side, and NH4 is a conjugate acid on this side. Same idea if we read this reaction backwards. If we go from NH4 to NH3, what's happening is NH4 is losing a hydrogen. It's acting as a proton donor. It's acting as an acid. So a base is always paired with a conjugate acid, and an acid is always paired with a conjugate base. Let's take a look at another example and see if we can figure out what the acid is and what the base is. So this one's a little bit easier because if you think about it, there's an H in front of here. We know this is hydrofluoric acid, but let's think about why it's an acid based off of Bronsted-Lowry's theory. So let's take a look and see how it's changing. It's HF on this side. It's F on this side. So what's happening is it's losing a hydrogen, it's losing a proton, therefore it's a proton donor, it's acting as an acid. Whereas water in this case, what's different about water? It's got 2 hydrogens on this side, it's got 3 hydrogens on this side, therefore it's gaining a hydrogen. It's acting as a proton acceptor, so it's a base. So let's take a look, and we have identified that we have our hydrofluoric acid is our acid, and we have our water is going to be our base. Now we want to take a look at the opposites. Well, here we have HF. Its opposite is going to be this F, right? We've lost that hydrogen. Remember, every acid has a conjugate base. So that means that this fluoride ion on this side is going to actually be a conjugate base. Whereas hydronium on this side, right, this here is a base. Well, every base has a conjugate acid, so therefore that would make hydronium our conjugate base. So let's go ahead and label this as our conjugate base, and let's go ahead and label this as our conjugate acid. Now, a great way to check is to make sure that this makes sense. So let's read this reaction in reverse. Let's start with our conjugate base on this side. If we read this reaction in reverse, we're going to find that F is gaining a hydrogen, right? We had F by itself. Now we've got HF. It's gaining a hydrogen. Anytime you're acting as a hydrogen or a proton acceptor, you're a conjugate base. Hydronium on the other side, we have 3 hydrogens on this side. We only have 2 hydrogens on this side. So if we read this reaction in reverse, H3O is giving up a hydrogen. It's acting as a proton donor. Therefore, it's acting as an acid. It's a conjugate acid. So here's a couple challenge questions. I want you to try them. I'm not going to take them up right now, but the answers are in the other slide. So go ahead, try the challenge questions and see if you can figure out which is the conjugate acid and which is the conjugate base. Some of them are easier. So for example, I can look at this and see this is a base, and I can look at this and see that this is an acid. Some of them are a little bit more challenging. Next up, I want to move on to our idea of pH and pH scale. So this is kind of the whole point of the note. We want to go through and we want to talk about what pH actually is and what it means in terms of acids and bases and how we actually measure it. So pH, this lowercase p and this capital H here, actually stands for the power of hydrogen, or sometimes you can have it referred to as potential hydrogen. So what it does is it measures acidity. So we place things on the pH scale based on how acidic they are. So something that's really low on the pH scale is considered to be really acidic. That's considered to be a strong acid. Something that's higher up, has a higher number on the pH scale, is actually not an acid at all. It's actually a base. So this H in pH actually stands for hydrogen. So things that are very, very acidic are going to have a certain strength of hydrogen, and things that are very, very, very not acidic or very basic have another strength of hydrogen. So you can actually go ahead and see that this is related to the concentration of hydrogen ions. So if we take a look at this scale here, 1 times 10 to the 0 compared to 1 times 10 to the negative 14, since this number is in the negative, this number is actually the smallest, and this number is actually the biggest. So the substances that have the highest concentration of hydrogen ions are said to be at the top of the pH scale, and the concentrations that have the lowest hydrogen ions are at the bottom of the pH scale. Again, this makes sense because something is going to be considered to be more acidic if it has lots of hydrogen ions, and something is going to be less acidic if it does not have a lot of hydrogen ions. Here's the issue with the pH scale. These numbers are so small, they actually really don't mean anything to you. If I said that a substance has 1 times 10 to the negative 14 concentration of hydrogen ions, it wouldn't mean anything to you. So we actually mathematically play with pH to make it a number that's easier for you to understand. So a solution with a hydrogen ion concentration of 10 to the negative 5 actually has a pH value of 5. So we just get rid of that 10 to the negative 5 part and we just call it 5. Compared to a solution that has a concentration of 10 to the negative 2, again, we just get rid of that 10, we get rid of that negative, and we just call that 2. So it's a little bit easier for you to understand that if something has a pH of 2, it's got more hydrogen ions. It's closer to the acidic end of that scale than something that has a pH of a 5. So something that has a lower pH is considered to be more acidic. Something that has a high pH is considered to be less acidic. Acidic solutions have a higher concentration of hydrogen ions, and a solution with a hydrogen ion concentration of 10 to the negative 7 or a pH of less than 7 is considered to be acidic. One example that we might want to look at, we're going to compare a solution with a concentration of 10 to the negative 5 mole per liter, and we're going to compare that to a solution of 10 to the negative 7 mole per liter. So if you take a look, we're going to convert these numbers. Let's start with 10 to the negative 5. If we're going to convert that to decimals, that's going to look like this here. That's a very small number. If we take this and convert it to decimals, it's an even smaller number. So the higher this number is, the higher this negative exponent is, the lower the number is actually going to be, the smaller the concentration of hydrogen ions in solution. An increase in pH by 1 is equivalent to a 10-fold decrease in hydrogen ion concentrations. So let's take a look at an example of that. Something that has a pH of 3 is said to have this concentration of hydrogen ions, 0.001. Something with a pH of 4 is said to have this hydrogen ion concentration, 0.0001. Notice that there's an extra 0 here compared to here. That represents a 10-fold decrease, right? So this number is smaller than this number up here, and it's smaller by a 10-fold difference. So that's pretty significant. So every time you take a step on the pH scale, the numbers are actually getting 10 times smaller every time that you go through. pH scale goes from 0 to 14. You can actually get lower than 0, and you can actually get higher than 14, but that's not very common. pH of 7 indicates a neutral solution. Anything that's less than 7 is said to be acidic, and anything that is greater than 7 is said to be, is said to be basic. If you add an acid to the water, the concentration of H3O ions increases and the concentrations of OH decreases. What does that mean? It means the lower the pH value, the greater H3 ions you have. So the lower your pH is, so a pH of 1 is one of the lowest values that you will have, the greater the H3O plus or H plus ion concentration is going to be in solution. If you add a base to a water, the concentration of OH is going to increase. If the concentration of OH is going to increase, the concentration of H3O is going to decrease. Again, what does this mean? It means that the higher the pH value you have, the lower the H3O plus ions are going to be. So the higher your pH is, so for example, 14 is one of the highest pHs you can have, the lower this value is going to be here. Each pH unit is 10 times as large as the previous one. So that means a change in 2 for the pH is 100 times more, a change in 3 is 1,000 times more, etc. So that pH is set by 10-time fold changes throughout. I'm going to let you read this on your own. This is a little bit about consumer products. What I want to get to now is the math part, and I want to focus on that 10-fold scale. So since there always is a change of 10, we actually say that the pH scale is said to be logarithmic. So you would have dealt with some logarithms in math class already. So if you're going to calculate pH, the formula to calculate pH is the negative log the concentration of hydronium ions. So the reason that it's a negative is, remember how every exponent we were looking at before was negative? By taking the negative log, you're getting rid of that negative sign. And what log is something to the base of 10. So essentially you're getting rid of that tenfold difference. So for example, something that's 10 to the negative 14 is we're looking at OH concentrations. Let's focus on H plus down here. So something that's said to be 10 to the 0 is just going to be 0 if you take a negative logarithm of it. Something that's 10 to the negative 1, if you take a negative logarithm, is just going to be 1. Something that's 10 to the negative 2 is just going to be 2. So this formula here essentially allows you to drop that 10 and to drop that negative. If we reverse this formula, if we want to figure out what the concentration of hydrogen ions is, all you need to do is take 10 and type in your calculator the negative pH. So for example, if the pH value is 1 and you want to find the concentration of hydronium ions, you would just type in 10 to the negative 1 in your calculator, and that would allow you to calculate the concentration of hydronium ions that are in solution. Same idea of the OH. We also have something called the POH scale, and that allows you to measure the concentration of hydroxide ions. So if you want to figure out the POH, you just take the negative logarithm. And if you want to figure out the concentration of hydroxide ions, you would just take 10 and with the exponent function on your calculator, type in the negative POH value, and that'll give you the concentration of hydroxide ions. So let's take a look at an example of a question that we could ask you. You've been told this: a solution with a pH of 1 has what concentration of hydronium ions? We're going to use this formula here. So in order to figure out our concentration, we're going to take 10 and we're going to punch in negative pH. So if we punch this into our calculator, we're going to find the concentration of hydronium ions is 0.1. And since it is a concentration, we're going to use the unit mole per liter. Let's take a look at another example. Let's take a look at a solution with a pH of 2. So same idea, we're going to use the exact same formula. This time, instead of typing in negative 1, we're going to type in negative 2 though, because that's our pH. And then we're going to find this concentration, 0.01. And again, because it's a concentration, it's going to be moles per liter. So notice here, this number, compared to this number here, it's a 10 times difference. So that represents that idea of that logarithmic scale. One really quick note about indicators. So indicators are a great visual representation to figure out if something is acidic or basic. So rather than going through and actually measuring the concentration of hydrogen ions in solution, which isn't always possible, we can just use an indicator to quickly determine if something is an acid or a base. So these are our indicators. Phenol red is a common one. Phenol red is going to be red only when there's a base present. It's going to change color. With an acid, it's going to go yellow. Bromothymol blue starts blue. Same thing, it's going to stay blue if it's a base, but it's going to change colors for an acid. It's going to go yellow. Red litmus paper is going to stay red in the presence of an acid, but it's going to go blue in the presence of a base. Blue litmus paper is same thing, going to stay blue with a base, but it's going to change color for an acid. It's going to go red. And phenolphthalein, that's a common one that we use. It's one that we would have used in your lab exam. Phenolphthalein starts colorless, so it would stay colorless if it's an acid, but phenolphthalein will turn pink in the presence of a base. So these are great visual clues, and they're great tools in chemistry for us to quickly determine an acid or a base. Acid rain, same thing. I'm going to let you read this on your own. It's something that's really important to understand, but it's pretty intuitive for you to figure out. It just talks about how the acid with certain gases might add to acid rain. And all that we've given here is a couple homework questions to help you practice calculating pH and help you identify conjugate acid-base pairs. Tune in tomorrow, and we're going to be talking about titrations, and we're going to look at how to calculate a titration and how to calculate the unknown concentration of an acid or a base.